For averages of large numbers, we have to adjust our thinking a little. Let's go back to our earlier example of 10 students taking a test. 9 students didn't care, and they got scores of 0. Hermione Granger got a score of 100. Now we draw this in a graph, or a histogram. We start to consider more kids taking the test. We're no longer looking at a special controlled, contrived example, but the real world. As more scores fill the histogram, we start to see a shape. This shape can be described by a mathematical function, a function that we can fit over the top of the histogram. This is called the limiting function. That means if we had an infinite number of kids taking this test, then the outline of the histogram would become the limiting function, meaning the more kids that take the test, the more the average, the mean, which is the sum of all the scores, divided by the number of the test takers, goes from a discrete function to a continuous one. In other words, the discrete steps become so fine that it is not helpful to distinguish them as steps. A good way to picture this concept is to think of a shape with a discrete number of sides attempting to represent a circle. We can start with 3 sides, a triangle, and then move to a square, then a pentagon, then a hexagon, and so forth, until we get to an infinite number of stepped sides of the polygon, which converges to a circle. The circle is the limiting function. Our histogram, or distribution of test scores, will not ever become the limiting function because we will not ever have an infinite number of kids, but it will approach the limiting function. The center of the distribution is as close to the true average value we can get. Let's think of the test in a slightly different manner. Instead of finding the average in a sea of scores, because we could calculate the average, it may take a significant amount of time, but it is possible to calculate. We instead want to find at what score the bell-shaped curve, the limiting function, is centered upon. This helps us to see the range of the majority of scores without putting too much focus on outliers, such as the high achievers, like the Hermione Grangers, or the low achievers, like the kids who don't care about the test. We can think of those low achievers as Crabbe and Goyle. The limiting function itself, for large numbers, is generally a bell curve, or a Gaussian or normal distribution, which looks like this. The bell curve equals an exponential raised to the power of negative x squared divided by 2 times sigma squared. In our case, we are interested in finding where the curve is centered. So we replace x with x minus the center. The center of this curve, of this limiting function, is what is commonly referred to as the average, the thing everyone wants their kids to be above. So recalling the original concept of this video, which was, why is it wrong to say, by definition, 1/2 of all people are above or below average, let's take a closer look at the concept of the average being the center of the bell curve. So the average is equal to the integral from negative infinity to plus infinity dx x exponential raised to negative x minus x center squared divided by 2 sigma squared. Inside this integral is the limiting function, the bell curve or the Gaussian, which is a symmetric function. So the average of the limiting function is at x center. Now this x center refers to the center of the limiting function. This is the thing that the measurements or the test scores will approach but will never reach, as in increases all the way to infinity. So looking at our equation for the bell curve and writing it out in English, what we have is the bell curve equals the exponential to the power of negative the scores, the horizontal axis, minus the average score, the center, squared, divided by 2 times the width of the bell-shaped curve squared. The value of the width of the bell shape, or sigma, is the standard deviation. This value is determined from fitting a curve to a distribution. The more outliers there are, the greater the value of sigma, the standard deviation, or the more wide the bell-shaped curve is. In other words, the less precise the measurements, or the less useful the concept of average. The standard deviation is a very useful concept when we want to think about what an average is, or at least what an average in the context of large numbers is. The probability of a measurement or a kid's test score falling within the area of the average minus the standard deviation to the average plus the standard deviation is given by this expression. The probability within a range of 2 sigma is equal to the integral, with the lower limit being the average minus the standard deviation, to the upper limit of the average plus the standard deviation, dx, exponential raised to the power negative x minus the average squared divided by 2 times the standard deviation squared. In more general terms, the probability to fall within some multiple of the standard deviation, this equation is called the error function. And it can be solved numerically, which returns a probability of 68% that the measurement or score will fall into a range of plus or minus 1 standard deviation away from the average, meaning that about 2/3 of people are actually within 1 standard deviation of the average, which is to say about 2/3 of people are statistically average. The misconception here is that the average of a Gaussian distribution is the place where it is centered, and the Gaussian bell curve is symmetric. So by definition, 1/2 of the bell curve is above average and 1/2 is below. But this refers to the limiting function, not the raw, real data or test scores, which approach the limiting function as in increases but cannot reach it unless we had an n equal to infinity. All of this just goes towards the delicious pedantry of correcting a perfectly reasonable statement which was most likely uttered to make you feel better.